time. Anyways, so what was I gonna say? Yeah, so there's like a subtle difference, right, between regular expressions and languages. Yeah, because the regular expressions just, yeah, it's the expression itself, not the language that accepts all strings that you can that are described by that expression, which are different. And so like then you're required to like make those subtle point type questions can be very hard. So yeah, I thought that was one of the harder questions for a lot of people.
Are there any like takeaways from that problem that you think would be helpful to know on the midterm?
I mean, the takeaway from that problem, I think, in my opinion, is an important thing just in math in general, which this basically is. Even if it doesn't have like, you're not doing like functions and stuff so much. Well, like you kind of are, because you can even think of the DFAs as describing functions, but the function being described by that's what's called a transition function.
Right.
But yeah, it's basically still mathematical type thinking. Here, you guys can close the door mostly. What was it? So basically, I would say the takeaway is maybe reviewing definitions and being careful that you're actually understanding each piece of the definition, right? Because like, if you look carefully at the definition of regular expression and the definition of a language, they're different things, and you don't have to do much work to connect them because they are very similar and they're very related, but you do have to do some, and if you don't know those two definitions, then you wouldn't be able to do that. There's also like a lot of just subtleties about definitions that you can really take advantage of in answering questions, sometimes significantly more simply. Things like understanding that when you take let's say for example you were asked to, what's a good one? Let me think of a good example. Let's say you have had a language, L, and you want to prove that you can intersect it with maybe some regular language so that the result has some property. Okay, so you're gonna, let's say this is given, and you want to intersect with some L prime that's regular that you get to come up with, such that, I don't know, maybe such that, let's call this just L double prime, is also regular, then this sort of problem could what if this is non-regular? Can I even guarantee this?
I don't think so, because isn't like complement and stuff like close under regular languages?
Complement is, so let's say, so I'm given, let's just, so this can be any language, regular or non-regular. I want to intersect it with something and get something that's regular and get something regular. Can I do that? And these sorts of questions are, the answer is like 3 letters. I mean 3 words. It's like 3 to 5 words, right? But these sorts of questions are in the practice problems. Like tons of the questions in the practice problems have very elegant answers, but they require you to see something about like the structure or know something about the definition of something like intersection. Because a lot of times there's like corner cases that basically answer the whole problem for you.
Can I like make a guess and say
Sure.
that that it is regular because if you intersect with something that's regular, then that language has to be in that intersection. I don't know if that makes any sense. So stuff that like overlaps.
That will not work.
Okay.
Why won't it work? Well, let's think of, because what if everything in here is in here, right? The regular language might just be a superset of this, in which case their intersection is just this, which we know might be non-regular. I'm not going to give an express example of how you can do that, but you definitely can. So here is, do you have any ideas as to what you could do to make this happen?
No.
Okay, so how does intersection work? What's the definition of intersection?
Oh, so it's like word in like, it's like a word such that it's in L and L prime.
That's right, yes. And what are some languages we know to be regular? So let's try and make this language. Want to try and make this language regular. So what are some? But I don't know anything about this, right?
Okay.
What are some general properties of languages though that make them regular?
They have a finite set of.
That's a really good
states.
one. Yeah.
They can be described by a regular expression.
So finite set of states, you already that's your
Oh, okay,
answer.
okay.
But why does that help you? Why does knowing that a language with it's not finite set of states, it's finite strings in the language, a finite number of elements in the language, right? So there's a finite number of strings in the language would mean that it is regular, right?
Oh, no.
Yes.
No, because like you have like a language that's just any number of eights are just repeating. That's an infinite language.
That's an
Right.
what so and this is a great point because this gets to another very important definition, which is implication, which is just like a logical rule.
Right.
Right. So what I'm saying is that if L is finite, and be careful, like what do I mean when L is finite? It's a set with finite elements, and those elements are just going to be strings. So there's a finite number of strings in this language. Then L is regular. What you said was if that might be a little too high. No, it's okay. For some reason, I should be writing bigger anyways. So what you said was if L is infinite, what I should really say is size of L. It's really number of elements in the set. Then it is not the case that L is not regular. So these statements aren't the same things. These can both be true without a contradiction, is the important thing. Right, and this is once again like just getting back to like being very careful as to what you're stating or what a definition means, right? Because if L is finite, that implies it's regular. But this isn't me saying that it's not. I'm not saying the opposite. What you were hearing is L is regular implies L is finite, which would contradict this, right?
Can we use this fact like without proof? For example, if you're given like a literal language, just a bunch of words.
Yeah.
Can we just say it's regular by by this definition?
It's in the lecture notes actually. That all finite languages are regular. You guys already have that, so you could use that on the midterm.
For one of the problems on the one of the exercise problems, we're given a language like that doesn't have a certain subword, a certain strings are subwords.
Okay.
So if we know that the complement of that is just the words that contain these subwords, and that's going to be a finite set, so the complement of it must also be finite. So it's going to be just like a two-line argument.
So yeah. So say it again. I'm almost positive you have the right answer. I just want to make Sure. So the question is what again? It's
So the question is like.
there's a
the
finite language,
Yeah,
and you
that-
want to accept the language of all strings that do not contain
these.
as a subword.
Yeah, so we know that the language that contains these subwords is regular, which is
Yes.
the complement of this. So the other way around should also be irregular.
So you have to be a bit more careful. You're going in the right direction, but the question is saying that it wants the language that accepts all strings that don't contain do you mind if I read the question
Sure.
just to be totally sure I'm getting it? But
Somewhere.
I don't, so which one? Do you know?
It's I think it's three.
It's 3B, right?
3B?
Yeah.
Okay. So we have L prime XY. We want to show L prime is the language of words in L with exactly one A deleted. So you're thinking of a slightly more
Oh, actually,
complicated question.
Sorry, I was thinking about a different question.
Okay.
It's sorry.
Because
Is it
B
2B?
E. This one is because this is
3E?
like a really like a literal this.
Yeah,
these
yeah.
three strings.
does not appear as a substring of X. You could do the more general thing you were saying, but let's focus on the slightly easier thing that's here. So X such that AAA, ABA, ABB, BBA does not appear as a substring. So no, what you were showing was that the language that is the complement of the language that contains AAA, ABA, ABB, and BBA is regular.
Yeah.
But this is slightly more complicated, right? Because this is saying I want to accept all strings that don't have this as a subword.
Yeah.
But you can still use the property you were talking about.
The finiteness.
Yeah. So what you could do is you need to show it's regular. So you could even use an NFA, where basically, what's the way to put this? Do I want to use an NFA here? So what's the easiest way to do this? So certainly the language of those four strings is regular.
Yeah.
Because it's finite.
Right.
Then what I can say is that so on a high level, the thing you want to be doing is you're going to make a machine that so what's the best way to put this? Basically, the way you would end up doing this is like you have a start state. In a drawing at least, would be this. Let's say we're just checking for the AAA substring. That's a trap state. These are accepts. Everything else is an accept state. And then these go back to the start state if they see anything else. And you can do that for each of them, right? So basically, your machine is checking for your machine is checking to see if So I think the easiest way to do this is to build an NFA for the complement language, which is to say all strings that do contain one of these three as a substring. I think that's the easiest way to go about it personally. So here's how. Let's see. Okay, so if I want to accept strings that have one of these four strings as a substring.
Could you potentially similar to how we did I think homework 2, where we from every state in our L, we can make an epsilon NFA and then see if it accepts one of those substrings and then go back and then
So there's a finite number of these strings, so you can make a separate and checking for any of these strings themselves. So what's the best way to put this? So because it's a finite language, there exists a DFA or NFA or whatever that accepts exactly these four strings, right? The problem is we don't know where they appear in the string we're looking at, right? So you can build a machine that basically has a start state Q0 that only goes to itself and is not an accept state. it epsilon transitions to a DFA. And then if it ever reaches, if it ever would accept, like if it would ever see any of these strings, it transitions instead to an accept state that is a trap state. I don't know, something. Does that make sense? So because the language that accepts those 4 strings is finite, we know there exists a DFA that accepts that language, like the language with just those 4 strings. So now what I want to do is accept the language that accepts any string that has any of those as a subword. So what I do is I build this state, which just does nothing. But this is basically the state of I have not seen a substring in the language yet. But at every point, it's epsilon transitioning here because it's like maybe it starts now. Maybe it starts now. Maybe it starts now. That substring, right? And then this DFA, we know it exists. And we're just going to say, if you would ever go to an accept state in the DFA, instead of going to the accept state, you go to this trap state that's an accept state. And so, because now you've seen one of the substrings, right? Does that make sense? Now this accepts the complement of that language.
Yeah.
And now you're done, because it's close under, regular languages are close under complement.
How would you go about proving this? In terms of
So the
writing it
proof,
down?
this is basically the proof would be a couple of steps. One, that the language that accepts those 4 strings, the language that includes those 4 strings as elements and nothing else, is regular because it is finite. Okay? That's like line 1 of your proof. And then line 2 of your proof is because it's regular, it has a DFA that accepts exactly these strings and nothing else. Right? Line 3 is it's closed under regular languages are closed under complement. So maybe you don't want to make that line 3. It doesn't really matter what order you do this in. So I guess, first line is language of those 4 strings is regular, then it's that they have a DFA that accepts those 4 strings. Next, you build this construction. You say, so consider this, now I want to show that there is an NFA for the complement of that language. So basically an NFA for the language of all strings X, such that X contains one of those 4 strings as a subword, as a substring. Right? So how do I do that? I build this state, and this can kind of be done here. The way you would prove that this machine does what you're saying, technically induction. But we do not expect that level of formality from it. Like you could define this machine in terms of its states, or you could draw it, or whatever. Probably the most formal thing to do would be to define it using the tuple.
Okay. So
Right.
Just to be sure, on the midterm, you wouldn't expect us to do an induction on this. It's just
No,
kind
we
of
won't
stating the
If you give
drivers and
if you give the tuple with all the correct modifications to the state, so the tuple here is that your new start state is Q0, and that its transitions are always to itself. Because do they even say it says one of those substrings. Do we even know the alphabet?
Isn't it just A and B?
Does it specify?
Yeah, it does at the top of number 3.
Yes, you're right. It says at the top of number 3. So we know, okay. So then you can specifically say A and B both bring it back to here, whatever. Make an epsilon transition to the DFA you know, to the start state of the DFA you know to exist. Right? It had some start state, so now you epsilon transition to it. It has some set of accept states. And you say, you make those not accept states anymore. You basically, all the accept states,
The epsilon transition.
yeah, there are many ways to do this, but the easiest way to do it is the epsilon transition. You add an epsilon transition from every accept state here to an accept state that's a trap state. Done. And it's pretty clear once you've done that level of formality that this does exactly what you're saying.
Yeah, because the reason I was confused because sometimes things are so obvious and I don't know how
Yeah.
to prove it. It's
Right.
It's
So
true.
the way to prove this would be induction.
Right.
And if you're concerned that you might be wrong about it, it's not a terrible thing to do, except when you're timed, it's tough. But formally proving these sorts of things, what's the way to put this? In mathematics, people the more complicated your math gets, the more people will accept you leaving things out, because it's expected that anything, let's say you're talking about, let's say you consider math as like levels of complexity. I'm way off the board. Doesn't really matter, honestly. If you consider like these as like various levels of complexity, like addition and subtraction, and then like divisibility stuff, and it just goes up and up. If you're talking about things up here, people are not going to expect you to be in like, well, and 6 times 9 is 9 plus 9 plus 9 plus 9 plus 9 plus 9. You know, like, there's an accepted level of like, okay, we're not talking about that anymore, and nobody has the time to tediously check those things. And you don't have the time to write those things. However, if you are unsure if your answer in something up here is right, going down one level to something more thorough can help you understand if your question is right. I mean, that's why math papers are wrong sometimes, right? It's because someone is working at a high level of complexity and misses, like clearly didn't actually do the rigorous steps. So, or they missed something in a rigorous step, like definitionally they missed some small corner case or something. Those are the sorts of ways math professors mess up. So yeah, if you're not totally sure if it does exactly what you're saying, you can always check it. And once you've done it enough times, you will be a lot more sure in the future about your constructions. Does that make sense? Because when you do the induction and you realize it's wrong, you will have gone through this process of finding where your construction was wrong and why it was wrong, and that'll give you a better understanding of when I construct these things, what are the things to look out for that can mess me up, that I wouldn't have seen. Does that make sense? So like when you're doing like homeworks and stuff, that can be a good exercise to go to an additional level of formality, but it's definitely not necessary if you're really confident this is doing what you're saying for the purposes of the midterm for sure. Then you just rigorously define it and you're done. Rigorously define it, say it does what you claim it does, and then the last step after that is, well, now you have an NFA for the complement of that language, closed under complement, that's regular. That is a DFA, because it is that is an NFA, so it's regular. Does that make sense? Cool. Do you have any questions?
Yeah, I had a question on the first problem. I don't know
Sure.
if you
Same.
You mind if I-
Same.
Yeah,
Which one?
it's
Sorry about that.
it's proving the transition function for
Uh-oh.
epsilon NFA.
Screen keeps blinking in and out.
Sorry, what happened?
I don't know.
You can look at
Might
mine
have died.
now.
Okay, it's fine.
Yeah.
Prove the following by induction for all x, y, q. I guess I'd probably do induction on the length of x and y combined.
Oh, I was just doing induction on the length of y, so that's probably why I was like not getting it.
Yeah, because then x can have an arbitrary length.
Yeah.
But I don't know. I think that's going to get worse. So certainly, the reason it's nice to do it on the length of x and y is because then you can say what's the base case?
Epsilon, or like y equals, or x, y, like the length is 0.
Exactly, right. And then you're going to have epsilons for both by definition, right?
Yeah.
Then as you do the inductive step, you know it's true for all x and y such that their total length is a certain amount.
Mm-hmm.
And you're saying, okay, now I'm going to consider ones with total length 1 greater,
Yeah,
right?
so you just add a character.
So what are the two cases? This now breaks down into 2 cases in your inductive step.
Oh, maybe like you keep x and then like you add 1 to y, or you keep y and then add 1 to x.
Yeah.
Okay.
Where either of them is 1 larger than they were previously.
Right. Okay.
Do we need to use the definition of epsilon closures at all within the proof?
What's the definition of epsilon closures?
Let me pull it up.
It's the union of all the states you can reach.
So my problem was like I didn't know how to go from the epsilon closure back to the form of delta.
Same.
So which is the thing we're talking about then? So I haven't read all these lecture notes. So
Well, this is the epsilon closure. So like if you're at a state in like XA, you can like start from X and then everything you can get to.
So you can start
X,
from X.
Question mark.
Start for any p such that So this, I'm just reading this part because I've
Uh-huh.
never seen the not over epsilon notation, so I just have
yeah,
to.
yeah, it's epsilon
I-
closure. I think.
Alright, so if W. Okay, that makes sense. So those are all the states you can transition to for free from Q. Because the problem is now you can be in a set of states, right?
Right.
After a certain
Yeah.
number of transitions, you're in a set of states, not necessarily a single state. W equals.
Oh,
But it
I see. What
will
you're
always
saying.
be a finite set of states.
That's true.
To be clear, right? Because there only are a finite set of
Yes.
states, even in an
Yeah, so the states you can get to, like from X, and then from all of those you
Yeah,
like add A.
Okay,
onto.
yeah. So basically, you should view the thing about this epsilon naught notation is you really need to view it as maybe the best way to think about it is as a function from your function to a set. Right? You've got this transition function on two variables, which is the state you started in and the string you're seeing. And now you're taking the epsilon, you're taking like the epsilon function of that, which is the set of states you could end up in by those transitions, and any number of uses of epsilon. So here's the way to maybe, I'm going to erase all of this if that's okay. I think we're good on this stuff. Oh wait, we didn't finish talking about this, did we? What's the answer to this one? So to recap, I was talking about the importance of like understanding rigorously like definitions as like just general advice for the midterm and math in general, is understanding rigorously, because we were talking about, which homework question was it? It was like one from last week.
Yeah.
Yeah, where it's a hard question because it's so subtle. It's like
Right.
asking you to say something about a very subtle difference between regular expressions and languages, which seem really similar, and they are similar and connected, but they aren't like the same thing.
Right.
So my question was I was pointing out just another case where knowing like understanding the way you can like use a definition to your advantage, like with intersection, can be very, very helpful, and honestly critical to solving certain questions. So let's say I give you a language L, and I ask, if I give you a language L, does there exist a L prime that's regular, such that the intersection of these two is regular? For any this. We get to pick this, but this could be anything. Could be non-regular.
What if you pick like L prime to be just like the set of like A, just like one symbol?
Yep, you're done.
Oh.
Because the intersection's finite.
Right. Because
Because the size of it's going to be bounded by the size of this.
Oh.
And it's just like, what is it? It's not the usual way you use intersection, but it's perfectly valid, right? Like it's, you just like, it's hard, I feel, because sometimes you're given these definitions and then you use them in a couple contexts, but that doesn't really give you the like, and I think sometimes when you use a definition only to solve a couple of different problems where it's like used in a specific context, you can kind of forget the full generality of how you're allowed to manipulate this definition, or exactly what this definition means. Like I think language was defined, but then you use language all over the place and in slightly different things like DFAs, NFAs, rigorously expressing them as sets, and you kind of start to forget exactly what the language definition actually said. And so by the time you get to regular expressions, you're like, why is this not a language? Do you mind grabbing the door? You're like, why is this not a language? But if you look back at the definition of a language, it's not. It's not a set of, strings. Right, because that's all languages.
Yeah.
And so remembering those things can be very important for various questions. You can always build your understanding of other things back up from basic definitions, but if you forget basic definitions, you can't build them from more complicated things usually. So, what was the new question we were discussing? Sorry, I wanted to get back to that before I erased
the
it.
epsilon closure stuff.
Right, yeah. So if I take, how does he write it? Did the delta have a hat or something?
Yeah.
Yeah.
With a hat.
Okay, delta hat. of, what was it, like
Q, and then XY.
and then, isn't it just X for the union one? If we're just looking at the original definition of epsilon closure for a sec, then we had Q of X or something.
QXA, I think. Like if the word equals like XA.
Yeah. So. So you, in a DFA, let's do it like this. In a DFA, if I said this is just a function, right, from Q, and let's say A is a symbol, so there's no way it's epsilon, it's just some single symbol in the language. This leads you from some state Q to something else, right? It's a function on two variables. I think it's best to maybe think of this as an entirely different sort of function. Because one is bringing you, or first one I showed you is bringing you, even if like you had X for like some string, in a DFA, it's bringing you from this state to some other state. Mm-hmm. This is bringing you from some state to some set of states. Right? And something that can be kind of confusing too is like, epsilon transitions are a little weird, right? Because you get an epsilon transition to some state here, but then epsilon itself, epsilon transitions to other states. Right? And I guess the way I would think about these transitions is if you're applying, let's see, what's the best way to say this? So once you, let's say this is Q, okay? I apply the epsilon transition, I get the set of, let's say this is Q0, and then we have Q, then I'm going to use, Q2, Q1, Q3, Q4. So this is the ugliest Q I've ever seen. Okay, so in this case, he's saying it's equal to what he's going to write as shorthand as this, right? But that itself equals a set of states. Doesn't equal a single state anymore.
That's Q not right? The closure of Q.
This?
Yeah.
Yeah. Good catch. Sorry. Right. Okay. Now, basically, how the transition function is working from then on is.
I have a question.
Mm-hmm.
Why aren't Q0, Q3, and Q4 included in the epsilon closure?
I'm trying to think. Let me check the exact definition. I think it is actually. But let me double check the definition. So.
I think anything you can get from
Only using epsilons, anything you can.
Right.
Get.
Yes, I think the extra stuff would also be there too.
So it's every single state then.
Yeah.
W is XA. W equals epsilon equals. Has he defined this earlier? I see. It's up here. Sorry, I missed definition 6.2. This helps me a lot. The epsilon closure is C.
So it includes itself,
By-
and then
If Q prime is in. Right. Yeah. Definitely. So it's defined inductively. So yeah, it's everything you can get to. You could also just alternatively define it one at a time, but this is honestly a better way to do it. Good. Makes sense. So now we're talking about struggling with the question that involves inductively, the number one, right, on the thing. Okay, so if we've got our base case, then both are epsilon, and so you can just use the, let's go, right, so here's a place you can use epsilon closure, right, which is that, how can we use epsilon closure here, so x, y concatenated, since they're both, we're talking about 1, and they were asking like how to do the induction, and I was saying I think you should do induction on the length of x, y together,
Oh.
as opposed to x or y is
Okay.
probably what it's not 100% sure that's right, but that is definitely what I'd gravitate to, and it makes your base case really easy, because then x, you know x and y, because they both have to be the empty string. So the left side is just going to be delta hat of q epsilon equals delta hat of qx of y. And so basically, if something is in delta hat of q epsilon, then you know because of the inductive definition, delta hat of the epsilon transition set with epsilon is going to be the same, because if there's a new thing in there, it would have been included inductively in the interior delta, right? Does that make sense? So let me write it all out.
Like if you already have the epsilon closure and then you like add epsilon to it, like you already have everything that you would have had.
Exactly.
Okay.
Yeah. You assume, you can do it by contradiction. You can say assume there is some new element here. Well, then it's in. Then there's an epsilon transition to it, in which case it's already in this. So contradiction. There's no new elements there. So you have q of epsilon equals delta hat. I'm gonna erase all this. I'm gonna erase this at least. Maybe I can keep the delta hat of q. No, delta hat of q of x of y. Right? But then these are equal to, in the base case, we have q of epsilon concatenated with epsilon, which is just this, is going to equal this. Right? These are obviously identical.
How?
Hmm?
Why obviously? Like how do we get there?
Sure. So your base case is length of xy equals 0.
Yes, but like from like the right hand side, like how
So-
are they equal?
Right, why are they equal
Yeah.
is what you're asking. Right, okay, so that I haven't said yet. So why are these equal? No, what I'm saying is these two are equal, because they are literally identical, right? The interior part here is equal to
Right.
this, right? Now from here, how would we show that they're equal? What's the method? We just went over it, but someone else.
Well, delta hat q of epsilon is just equal to q. If you have anything with this, not like the element is epsilon, then it just takes you to that state. Or I guess
So
it
we wanna
takes
use
you to
epsilon
the-
closure.
The closure. Yeah.
Right. So what would make these not equal? We know these parts are equal. It would be if this transition added something, right, to this set of states that this includes, right? But now let's do a proof by contradiction. So assume these are not equal.
Mhm.
Then delta of this of epsilon must include some additional state.
Oh,
But because it's because epsilon closure itself is an inductive definition, then if this adds some state, then that state should already have been included here. Does that make sense? It's because it's basically like saying this. It's like it can't be that, like, let's say that you're now here, that this like set that this is in, let's say Q1 is in this set. Is in this set, but Q3 is not. Okay, and let's claim Q3 is in this set, but not this set. Okay? Well, that makes no sense, because me saying this adds it into the set means that there was an epsilon transition from something in this set to here. But if there's an epsilon transition from something in this set to anywhere, it should already be in here, because that's the inductive definition under epsilon closure. Right? Does that make sense? Like if you can follow another epsilon transition from something in here to get something else, then by this definition already it should already be in there.
Is that like obvious enough that we can like skip the proof, like, or
No, I mean I would definitely just
Or could you just like explain?
you I think you can explain it, but like look at epsilon closure and look at epsilon closure definition, and I would say be like, okay, well, you know, because really it's just as simple as the contradiction proof I mentioned, right? It's say assume that these two are unequal, then there must be some. This is a set of states, right? And this is a set of states. So it must be the case that this outer delta can take as input this set of states and epsilon and get from some state in this set to some state not in this set via an epsilon transition. That's the only way these two would be not equal, right? Okay, because if there's no epsilon transition from anything in this set to any new state, then this part doesn't add anything to the set, right? Because that's the only time it adds things to it would make the set bigger. Does that make sense? So let's assume that happens, that at least one state in this set has an epsilon transition to something else. But then it would already be in this set. But then it's a contradiction that this is, you know, it's a contradiction of epsilon closure. Because this, by the definition of epsilon closure, should contain everything you can get to from any number of epsilons from Q, using any number of epsilons from Q. So if there was a state in this set that had an epsilon transition somewhere else, it should be in the set now. There's your contradiction. So this can't add anything. And so that is, does that make sense? Yeah. So that's pretty formal. I mean, you don't have to state exactly, like, you can write it in symbols, or you can write it kind of the way I described in English, whatever feels most comfortable to you. But I would say in general, if you're writing a proof and you aren't convinced, like it gets back to what I was saying about like mathematicians messing up sometimes, which is like, when you write a proof, seriously consider if you believe your own proof. And if you don't, then look at what parts you're shaky on, and you should know how to prove those parts. I'm not necessarily saying you should write them, like that you should always prove those parts, but if you don't see how to prove simpler elements of your proof, then it means you would have trouble detecting if your proof was wrong in the first place. Right? Like if I try and prove something in some high-level math, and I realize I don't know how to prove certain substatements, then I can't check the validity of those substatements, and those could just be wrong. Does that make some sense? Yeah.
a lot of sense, yeah.
It's like debugging proof.
Oh my god.
Now we're talking.
Okay, so this is the base case. Does that make sense? Anyone have any ideas for the inductive step from here?
Okay, well, obviously we need an inductive hypothesis.
Okay, so my inductive hypothesis is what?
Is that that top statement holds for x, y, like the length of that equals k.
Yeah. Give me 1 sec. I'm gonna move this over because it's just off the screen. Where do I have till? I think I can erase this now. I just wanted to use it as a visual for all these epsilons for a sec. Okay. Apologize if I spell anything wrong. Because I am a horrible speller. Whatever. Okay. Inductive hypothesis. What's our inductive hypothesis?
assume for
Length of x, y is k.
okay that like
I'm just gonna write that this holds
Okay, yeah.
because it's just
That-
it's this statement
Yeah.
that this. You want to use K?
Use N.
N works too.
For what letter?
Whatever letter you feel like. Anyway. Okay. Now we need to prove for n plus 1, right?
So take x, y, a, add an element onto it.
Right. But the element could be in x or in y,
Yeah.
right?
Or on either side, right? Like,
Yeah.
Do you have to do it for all? I
The
guess
thing
it could be
is-
in between it too.
The thing is, you're gonna break up the string at the end of the day, right? Like, what's the way to put this? Equals x, y. So I guess this is saying this has to hold true for any way you break up the string.
But I think that it shouldn't matter where you put it because then you would just shift your x and y.
Mhm.
So then you can just prove it for
Like one case.
one case.
Yeah. I think basically what you're gonna end up doing is you're gonna use like kind of the ability of transition because if you look at like epsilon closure even, for example, right, it has that part where it has that last a that it so right. So you can even look at the definition of epsilon closure where it has that like last extra symbol, and then you could I think you could basically just do
You can just add an A onto the end of it, right?
yeah.
And then like any like from all the states that you can get to from X to Y, then just like add A onto it like from all those states.
Yeah. Basically.
Okay. I guess that makes sense.
People want me to do it out?
No.
Or is it, or you guys think that, kind of like, I think the important part is I don't really know what let's see, is there a way to do this is there a way to do this by just doing induction on one of the variables?
Where do you take into account epsilon closures?
Epsilon closure comes into play right here, in the base case.
Only in the base case? You don't have to do it in the inductive
Um,
stuff?
I'm not sure, I have to think about it for a
Because then
second.
I think we already did this in the homework then.
Yeah, I think you've done something extremely similar in the homework.
I think we just did this.
Yeah, because now you're adding an extra symbol. You don't even have to worry about epsilon as much anymore. And I think your inductive hypothesis should be usable anytime you would have to consider epsilon. Really, right? Because you're adding one new symbol, and then you just don't care what x and y are. X and y can be epsilons.
Yeah.
And you should have covered that in your inductive hypothesis at this point, so you shouldn't have to go back. And
Okay.
I think you're kind of done with epsilon closure at that point. Let me think about if you can do induction on one of the variables and still do a base case that makes this not so bad. So let's say we know the size of y is 0, or let's say the size of x is 0. Oof. Size of x is epsilon. Let's see. Yeah, I don't see as nice a way to do it if you just try and do induction on one of them. The inductive step is a tiny bit weird. So for the inductive step, one extra length. It's gonna be I think you might still need epsilon closure. Let's see. Because the problem with your extra symbol too is like you can just append an epsilon after the extra symbol,
Oh, that's true.
right? So it's like you can go to that next state, but you can also go to everything that you can epsilon transition to from that next state. And so I think you have to be a bit careful with like,
But I think similarly to the base case.
Yeah. I think the important thing is,
starting at the same state, then
Yeah.
it's the same epsilon quotient.
and I think the important thing to do is just like add a new symbol, A. Let's see. The only. Yeah, because Y can be empty. You basically probably want to add an A to the end of the string. But you still end up with two cases, sort of, where it's A is in the second one, where it appends to Y. Or
It's on X.
or everything is in the first, or Y is empty.
Y is empty. Why would
Yeah, so basically, think about it like this. I want to show that this holds no matter how I split up your string,
Yeah.
right? So if let's say I assume that now I know it's true for X and Y such that their total length is N.
Yeah.
But now I want to consider adding another symbol, A, to make it
N plus 1.
Yeah. So you had some string of length N, and I'm going to add a symbol to it, so when I break it up, it will, the total length will now be N plus 1. But let's assume I added the new symbol for the N. Let's assume it's true for no matter how I break up the first two parts.
Yeah.
But now I'm going to add an extra symbol A.
Mhm.
Where does the A go?
Yeah.
It basically goes on the end of Y,
Mhm.
but
Mhm.
it might also go on the end of X, in which case your Y over here is like empty, right?
Also, couldn't it go before A or before X? Like, you
Better
could
just to assume. So I think it's easier to not think about that.
Okay.
Those sorts of cases, right? Because we don't have to.
But then why do you have to take into account one of those cases?
So the thing is, I'm trying to prove that for a string of length N plus 1,
Mhm.
no matter how I break it up
Mhm.
between these two functions,
Mhm.
I think the important thing to think about it is, imagine I have like an X and Y that I know it's true for.
Yeah.
What I really want to come up with is like an X prime and Y prime that it's true for.
Yeah.
And I know the size of these equals N, and the
Mhm.
size of these equals N plus 1.
Yeah.
Now, I can split up X prime. I need to be able to, no matter how I split these up, split this string, have this work.
Yeah.
So what it could be is, we know all the ways that split this work.
Yeah.
So I basically want to be able to say that X prime equals, unless Y equals empty in the first one, then X equals X prime, and YA, which is, this is
Yeah.
a symbol.
Mhm.
This, yeah, like some letter. I don't remember the terminology he uses for just an element of the alphabet. Equals Y prime.
Yeah.
But I can't use this generally because this implies that Y prime is non-empty, which we don't actually know.
But I can also be within Y.
Unless Y prime is empty. That's what I care about.
I can also be within the Y string itself. It doesn't have to be.
Let's
on
assume
the
it's not.
side.
We don't need to put it in Y, right? Because, what am I trying to prove? I know that this relationship holds. I know that for any string of length N, no matter how I divide it into X and Y, that this statement holds, right?
Right.
Here, what I'm trying to say is the same thing, but for strings of length N plus 1. So I now have some string of length N plus 1, and I want to define this in such a way that I'm going to be able to use my inductive hypothesis.
But like that extra character you're adding, it could be anywhere within this XY string. Because all of
It's not the best way to think about it. Think about it like this. If I give you a string of length N plus 1, and now I stop considering the last character. How long is the string I'm looking at? Length n. And I know that this string has this property, that if I split it up and treat the transition function either way, that this will hold.
Okay.
So it's less of you're adding an extra character and more that you're taking your string of length n plus 1 and you're looking at the first n and saying, I know the property holds for these. Does that make sense? Right. So now, kind of by assumption, now I'm going to, I need to split it up into an x prime and y prime. But I'm going to say, okay, well, that was first n characters. We already know you can split them up any way you like, and it still works. Now what I want to say is, no matter where the last character ended up, which is either at the end of y, at the end of this y prime is always going to have this a, unless there's always the possibility the way I split this string is I put everything into x prime, right? In which case, the last character is also in x prime. But any other way of splitting it will leave a in y prime. Does that make sense? Right. So where do we go from here? So now, let's consider, what is the easy case?
Wait, so there's, just to be clear, we have to do two cases where A is at the end of Y and where A is at the end of X, or do we have to do a third one where Y is empty?
No, just two cases.
Just the two?
Yeah. So, because y being empty doesn't really matter. If y is empty, then y prime equals a, and that's fine. Okay, but how do we...
I think you use the way to split up delta hat, where delta hat, at least for the case of where x, y, a, where a is at the end of y.
Yeah. We're going to use it internally here, I guess. Yeah, that makes sense.
I said
Yep.
that delta hat of q, x, y, a equals delta of delta hat of q, x, y, comma a, where you
Yeah.
and then that's where you use the
That's where you use your inductive hypothesis.
Yeah,
Yep.
and then you just undo that to
Right.
bring the a back into the y.
That makes perfect sense. Yeah, that's seems like exactly right.
And then I think for
And having the a at the end makes this sort of, you know where the a is.
Yeah.
Like doing it in this way means you have flexibility in that manner.
and then I think you do just
And then the other case is a little weird. The other case you do, I think, have to go back to epsilon closure actually.
oh really?
I think so. Let me think about it for a second. So if everything is in x prime, then y is empty string.
Oh yeah.
Y prime is the empty string. They disappear. And then we use epsilon closure to get rid of this again.
Wait, sorry, can you say that again?
Sure. So let's say, the first case where this is what's happening, you were totally right. You take this, you know that, but everything could be in x could be empty. Does that matter? Does x prime being empty screw us over a little bit? Because one of the challenging things is what if x prime, I think there might be a third case. Give me 1 sec to think about this. I feel like I'm overcomplicating this problem, but maybe I'm not.
I feel like on a midterm they wouldn't like.
They're not gonna ask
you
expect us
something
to
this
do
hard.
these like corner cases.
Yeah.
I
So I feel
really,
like if I get most of the points, I'm like kind of happy.
I don't think there's any way. Let me think. Could you get asked such a difficult question?
I don't think so.
I think this is
Not on a
beyond the scope
midterm,
of the
yeah.
midterm questions. Yeah, I've seen the midterm, so you know.
So what's on it?
So I'm just gonna say that writing a formal proof to a question, I'm not saying like the nature of this question might come up, but I don't think you'd have to write such a long proof for
Right, with like every
anything.
single corner case.
Yeah.
I feel like that's kind of
Right,
extra.
because so here's the problem: if x prime or y prime has everything, then you can't apply your inductive hypothesis anymore, right? Because your delta, either your interior or exterior delta has n plus 1 characters here,
Right.
right? If either x prime or y prime is non-empty, then you can apply your inductive hypothesis either to this one or this one, right? Does that make sense?
You're not actually assuming it's for your string of n+1, you're not actually assuming it's the same x and y added in A. You simplify it
Right.
that way, but it doesn't have to be.
It doesn't have to be. There's
Okay.
2 corner cases that don't allow me to use this
Okay.
simplification
Okay.
criteria, right?
That makes sense.
Because, yeah.
So you just
Because
ignore 'em?
I can't just put, I wouldn't ignore them in a homework question. Like, if I asked this question, I would definitely expect students to go over the corner cases, and I would dock a couple points for missing, maybe like 1 point for each case or something.
I'm good with missing 2 points.
But, like-
it's not.
But, you know, everyone has different grading criteria, so don't assume I'm grading it, but like, I think someone could reasonably dock 2 points for each case, which would be a lot more significant. Because these are like the hard cases in some sense, so sometimes, depending on how graders do it, I tend to try and give fairly uniform credit for each part, which means missing the hard part doesn't dock many points. Other people, though, see the hard part as the core of the question and thus give more points for that part. But anyways, I think you can basically just use epsilon closure again on those parts, because then one of them is epsilon. Does that make sense? So if you can't apply your inductive hypothesis, it's because there's either an epsilon here or an epsilon here, and then you can use epsilon
Then
closure.
would it make more sense to do induction on either x or y, not x, y, because then you don't have to take in as many cases into account?
Maybe. But then your base case is interesting. So yeah, maybe that would be easier now that I'm looking at the final answer.
'Cause your
Both will definitely lead you to the right solution, but if you assume that x, let's say for your base case that x is epsilon, then you can kind of apply epsilon closure still immediately. Okay? And now we're saying that the size of x is 1 greater in the inductive step. Oh my. How do you deal with that at that point?
if x is only 1
If x, yeah, size of x is 1 greater.
You just take everything like you can get to, like anywhere you can get to from x, and then add that character on, and then that's.
you might
where
still
size
have to
of
take
x
into
is 1
epsilon
greater.
because y could still be epsilon then.
This seems tough because now you're like forcing yourself into one of these cases, right?
Yeah.
Which is that you can't apply your inductive hypothesis.
Yeah.
You've actually like directed yourself directly at the worst cases of this
Yeah.
example.
Yikes.
Does that make sense?
Yeah.
I generally find when there's multiple variables that it is most easy to do inductive on their total sum. I think we've talked about this actually in a previous office hour, where there were like multiple variables going on, and what was the induction question? Did you ask an induction question like 2 weeks ago? That was. I'm trying to remember. What was the induction on that was weird?
Oh, was it the first homework maybe?
I think it might have been the first homework.
That was this problem then. It was the
Yeah, it was about this for like DFAs,
Yeah.
essentially.
Mhm.
And so, yeah. But trying to just like take all of the variables at once if you can, and doing induction on their sum usually makes things easier, because otherwise you essentially have to do nested inductions sometimes. Sometimes you need to do that, I think. But like trying to do, I'm going to induct on X, and then I'm going to say for every induction on X, I do an induction on Y, which is something you can do, which is also sounds terrible, right? It's like for every size of X, I want to say that
Please
every size of
don't put that
Y
on
this works, but like that generally doesn't sound fun to me, and so I avoid it.
Recursive induction.
Yes,
Oh
you
my
can do this. You can nest inductions any number of times. Can you induct over an infinite induction? Infinitely nested inductions.
Yikes.
I think that's beyond the scope of this class.
That's beyond the scope of this class, that's for sure. I think we can
I hope
safely
so.
ignore it for the midterm.
Can I ask a question about a
Sure.
different one?
Yep.
For in problem just 2, and I guess it comes up, I don't know, maybe only in problem 2. When we're supposed to do DFAs, NFA, or regular expressions for when something does not contain something, how, I could see how you could do it with a regular expression where you just like add in the closure on top of the symbols, but then how do you create a DFA or an NFA that does not include something?
Sorry, I got distracted by the email. Can you say it one more time? I missed
For
something.
when we're supposed to construct like a DFA or an NFA
Mhm.
for a language where the only requirement is that it doesn't contain something, how should we construct? Oh, would
That
you
it
just
doesn't
like make
contain
a
what?
trap state?
You
Like
mean
a
that it doesn't?
subword.
As you're talking about the AAA.
Yeah, either
Yeah.
A, B, B,
We
or
talked
the,
about that one for a while, so I
Oh,
don't
you
actually
did?
want to
Oh, okay.
rehash
Then
that
I'll
one too
look
much.
back. Okay.
If that's all right, since we're already over, so I can't answer that many more questions. I'll stay till about 1:30-ish, maybe a little longer, but
Can I ask a question about the Fibonacci's? Because there are like two of them.
sure.
So are we just doing like kind of strong induction on the structure Fibonacci word?
It's actually the first thing. Is it the first thing we talked about? Her question today. This.
Fibonacci word.
No. Her question on the AAA, like.
Oh yeah, it was one of the first.
I think it was
things.
almost. It was. It'll be very
Okay.
early in the video, and I'll
Yeah.
upload it much faster this time. Sorry about that.
So we have like the second question. Oh, sorry. The third question is this guy.
Sorry?
So we're just showing that
Mm-hmm.
this is
when
the and then
he
also
does
have we want to show that
upload
it's
them,
not
where
regular.
Okay, can we go back up
It
to it for a sec? I want to
should
just
go
read
to-
it. Run recursively where you can
Piazza.
concatenate the previous string.
Yeah. Then
I see. So the new string comes
he
out in front.
posts
okay.
the link.
Thanks.
So I mean, it's going to be pumping llama.
Oh, this one?
Proving that it's not regular.
Yeah.
Proving that it's
Right.
I'm not sure you guys literally know almost any other tools. There's Mahale in the Road or whatever, but like that is not expected for the midterm, and so it
Okay.
wouldn't be in these examples. So you should assume that when someone's like, "Show this is not regular," it's pumping llama. Like there's almost nothing. There's really nothing else it could be. So
And for this other one, we just use like strong induction.
so now let's go down to the question.
Yeah, use strong induction for 3, like the Fibonacci words.
Oh, sorry, I didn't read the question. I was more just looking at the definition. Did you want?
So this is this is.
Fn does not contain the substring 1, 1, or 0, 0. Right. Yeah, so you would just use induction. That's definitely right. Because,
Cause like if the one before it and then the one before that like don't have those substrings and concatenating them won't
Yeah.
give you the sub. That's
Yeah,
kind of
yeah,
like,
exactly.
Not necessarily. That's the problem. Because like if one of them, I mean, obviously it doesn't contain it, but like I don't think making that assumption in the proof would. I mean, we need to justify it.
It's
Because like there are multiple cases, one can end with 0, 1 or 1, 0. So like one can say, okay, what if the other one is ending with 0, 0, and then this is 1, 0. This is gonna be 3 zeros, right? So I'm
Yeah,
not sure like how we kind of show
I
that.
see what you're saying. It is not in general the case that concatenating two strings that don't contain these substrings
okay, right.
is not going to contain these substrings.
But could you talk about the proper like if just like looking at the pattern you could say like
Just looking at the pattern is usually a recipe for disaster. It's usually a good way to start.
okay.
It's usually a bad way to prove.
Okay.
If that makes sense.
Okay.
Like because because
Alright.
it's not formal. It's definitely
Right,
the way to
right.
find how to get the proof, but it's not.
You kind of have
formal
to do
enough.
induction on. If you want to prove it for n+1, you have to assume it holds for n and n-1.
Yeah, so strong induction.
Right.
Oh, okay, sorry.
I mean,
Or I don't know.
they're basically the same thing. Honestly,
Yeah,
like
that's
induction and strong induction, I almost don't even like that they're taught separately.
Fair.
I would say, I think I literally spent like 15 minutes in an office hour last year just explaining why strong induction doesn't need a base case.
Oh.
Because like people, anyways. There's like subtleties in their definitions that are a little weird, but yeah, strong induction is probably the way to go. Just assume that it's true for all n less than whatever you're talking about. And then you want to prove for n. Do you want to prove something stronger? Okay, so your observation is good, but let's take the observation a step further and ask the question, okay, so it's not the case that two strings that don't contain those substrings don't contain those substrings when concatenated together, right?
Yeah.
What about the strings that you see make that true?
Because they always start with 0, and the ending alternates.
Yes.
Because of the base case.
Exactly. Right. So there's always a single 0 on either end, no problem, followed by a 1.
Right.
On either end. And those, if you concatenate them together, what happens?
It's always gonna be like a 1-0. It's never gonna be a 1-1.
So let's think about it like this. It's honestly easiest to. Can I erase this actually? We
Yes.
good on this? I just hope I didn't miss an easy trick to deal with these cases. I might have. I'll think about it later. But they really do seem like you. And I don't think it's that bad once you see it, right? You just use the epsilon closure on the cases where you can't apply your inductive hypothesis. Yeah, that seems fine.
I have a question real quick. So, is there gonna be like a solution posted for these practice problems so we can like check our
That'd be
answers?
great.
He said no.
Oh dang.
No.
Okay.
This is that moment.
Oh, okay. Can I like DM you and like check my or like?
You could throw it on Piazza,
Okay.
and either one of the other, either me, Jafar,
Uh-huh.
the professor, or a helpful student, preferably a helpful student.
Uh-huh.
What was it? Yeah, someone will answer it.
Okay.
There's also
Hopefully.
like a Piazza post on like crowdsourcing answers.
Oh
So
really? Oh,
that's,
fantastic.
yeah.
Okay.
Okay, so, sorry, I lost my train of thought. Okay, so the Fibonacci's, what have we observed? We've observed that this happens not because they don't contain that substring. This happens because they have the following property. Right? Other than the first few cases, which of course do not have any characters here, because it's, 1, 0, 1, or 0, 0, 1, or
Yeah.
0, 1, 0. So those ones don't have this, but you have those already down. And so, everything that's not on that paper has this form.
Except not all of them end in 0.
Yeah, it could be 0-1 or
Or
1-0.
1.
Sure.
Yeah.
So it's either this,
Or like,
or it's, what was it,
0-1 and then it ends with 0-1.
with,
0-1.
okay. So,
Can you basically just say like there's no way?
I mean, you should just do induction, but your base case is everything written there,
Yeah.
because they don't contain the substring. So he did your base cases, he did a lot of base cases.
Yeah.
And now, it doesn't even really matter which ones you take. You could even take the same two twice. Take any of your take anything previously.
Mhm.
If they have these two forms, what's going to be their final? What's going to be the form of? How many cases are there? Let's just literally make this a harder problem in
Okay.
some sense, and not think of it as the last two strings.
only 2.
There
4,
are.
right? Isn't it 4? Because like that one could
Yeah,
be
there's
first
4
and
cases.
that one. Okay.
But it either,
Sort
they
of.
always
And
start
it's really
with 0.
there's
It always
4
starts
cases.
with a 0 and either ends with a 1 or a 0.
But which one is concatenated to which one? Which one is?
Oh, okay.
It's the
Yeah,
direction
yeah,
of
yeah.
concatenation that
Mhm.
doubles it again.
So
Yeah.
just like 2 quick questions. Like first, how does this relate to regular languages, like in topics we've been studying?
Mhm.
And second, like how obvious is it that we make this observation that these words will always have this form, and we
How
don't. know.
obvious is it?
Yeah, I mean, like, who knows that there could be like other words that have a different ending. Like, what's our justification for this? Like saying, oh, they always have
Okay.
this form.
So everyone you see on there has that form,
Right.
right? Okay. So every other string in the Fibonacci sequence is generated by two strings that they're concatenated together, or 2 future strings concatenated together. So let's talk about all the strings that are generated only by base cases concatenated together. That's sort of our base case, really, is like, so for any of the 2 listed there, they're going to have this form, right? So, or they're going to be one of the, like, early ones, like, but actually,
So really you're doing induction on the form of the string.
yeah.
Well, you're doing like 2 inductions.
Yep. I'm honestly making it a little more complicated than it needs to be. Let me look at the question, because I think we can make this even easier, which is that it alternates, right?
Yeah.
Yeah. Okay. The ends alternate. So really, you don't even. Which is the last ones have which form? So we can do our induction starting at F5 and F6, right? Because we can start with F7. That's what we want to work on, and it's going to be this concatenated, this with this concatenated at the end, right? That's the first case that we're going to deal with, is getting F7. And
Oh, so there's actually really 2 cases.
You're right. That's why I was saying it's simpler for Fibonacci's, because he's not grabbing arbitrary things from there. He's taking it's going to be in a specific. It's going to alternate. Yeah. And so you can do F7, and then you can do F8 by hand, and then the induction is almost trivial from there. So basically, you do this one, and you get what? You get 0, 1. We know this doesn't contain any of those substrings. Right? Which is of the form. Right? And now for the next one, I'm going to concatenate this to the end of this, right? And I will make a similar observation that it alternated again. And now I say assume that, like my inductive hypothesis, I guess, is that for even numbered Fibonacci's, you're doing this concatenation. Sorry, for odd numbered Fibonacci's, you're doing this concatenation. For even numbered Fibonacci's, you're doing that concatenation. And I guess my sort of base case, you could honestly, I think you can do the funny thing is you can actually do your whole base case with things he wrote. It's easier to not start at these ones. So let's say that my inductive hypothesis is that for odds 3 or greater, they have this property. And or the inductions I want to do is, for Fibonacci numbers with odd index, they're going to have 0, 1 at the start and 0, 1 at the end. For Fibonacci's of even index, they're going to have 0, 1 at the start and 1, 0 at the end. And he actually has already done them, right? Because you can take, But then every Fibonacci is generated from 2 of these. Is that the easiest way to do this? Ugh, there's so many ways to do this induction. I can't decide which one's easiest. But I want to come up with one that I really think, because I feel like he's basically given you a base case, and I want to use it. I'm almost tempted to drift back to the possibility that they could be in any order. It's almost easier, because then you don't have to worry about evens or odds. You could just say, for every Fibonacci number greater than some amount, let's say 5, it's the concatenation of 2 strings. If it's the concatenation of 2 strings of this form, and so you will get something of that form, of one of the 2 forms. And neither of these contain, and it just happens that neither of these contain those substrings. And then your base case is done, because you look at like 5 and you see it's the concatenation of 2 such strings, and it yields something that is one of these 2 such strings. And then for something else, you're like, assume this is always true for, n minus 1 and n minus 2. Then f sub n minus 1 and f sub n minus 2 have these forms. And notice that whatever I get out from any combination of these in any order has this form, and thus I'm done. So I think that you could prove something stronger. You could prove that these are alternating, right? But that's not really necessary, and I think it's actually more annoying. Does that make sense? So I kind of actually want to go back to our original way of doing it, because otherwise you have to worry about proving something stronger about the Fibonacci sequence, and I just don't care. Because it's not relevant for what you're trying to show.
Oh, total non sequitur. Is binary going to be on the test? Will we need to know binary very well?
Oh, like base 2?
Yeah.
Even if it were on the exam, I think it would be very minor, and it would be very easy base 2.
Okay.
So, if there's any don't feel like you have to be a base 2 expert. Don't start doing times table sorts of things like base 2 tables.
Yeah, okay.
Base 2 to base 10 tables, it's not what you should be worried about.
Yeah.
If it's there, I think, and you didn't get a 0 on that question, on the homework, I think it'll be okay.
Okay, cool.
Yeah. That's as much as I'm going to say on that. Does anyone else have any other questions? Do I have a few minutes? Yeah, I could answer one more. If anyone.
Oh, this is like very quick. So.
Oh, but you had a question. Did you have a question about proving it was not regular, as well, the Fibonacci stuff? Because you said there were two
yeah,
things.
you answered that. Thank you.
Oh, I did. Okay, cool.
Yeah. So,
Pumping lemma. That's the
Yeah.
answer. Yeah.
So 3, we have like a couple of languages, and I think they are equivalent to the ones we proved in the homework. So I just want to make sure. So
Sure,
like
let me-
3C, like this is the minus. So this is the language of suffixes, right?
Yeah.
Mm-hmm.
And in this other one, and this is also, I think, the language of prefixes. This
So which one is the language of suffixes?
this minus
That
L.
is. Oh.
And this other one, I think, is the language of prefixes. Oh, it's similar to that, but yeah, it's just with this extra condition. And this other one is
So the-
this insertion, which we also
Didn't you do the opposite of this in class?
right?
Mm-hmm.
It's very close.
Yeah.
But it's reversed, right? U and X would be
Right.
in different places.
Right.
Because yeah. So that's the difference. So this one is different from class only because the U and X have swapped places.
And this one, like, I mean, this is insertion, so like we already proved that insertion is regular.
No,
so
this is not insertion.
we
actually.
inserting like
This is deletion. This string is in L. It's saying X, A, Y is in L. This is the language of every string in, so L prime is, so we're talking about 3B? Yeah, 3B.
right.
L prime is every string in L,
Mhm.
except that it had at least one A deleted. It had like one A
isn't it
deleted.
equal like L prime equals to L with the language containing only A inserted into it, like another equivalent.
So this is not insertion. If I was asking an insertion question, then basically what it would say is L prime is all the strings from L,
Mhm.
except with an A put somewhere in the middle of the string. This is saying it's all the strings from L prime that had an A
Okay.
that is now gone,
Mm-hmm.
right?
So that's just gonna be an epsilon
How do
transition.
you deal with the case
Yeah.
if there are two A's in the word in L?
Then if deleting a single one, any single one of them,
Mm-hmm. Gives different words.
then yeah. So
Mhm.
basically, if you had a word in L that had 3 A's,
You just need to
this
delete one and
could
then
this
that's
could
fine.
generate as many as 3 words
Yeah.
in L prime, but it may only generate 1.
So as long as you delete
Why?
one.
Well, here, so let's see why this is the case, and this is
Shouldn't it
interesting.
Have to do all 3.
So you don't have to delete. So okay,
Well, there'd be 3 different cases.
there are 3 different cases where you delete 3 different A's.
Yeah.
But why don't those result in different strings in L prime necessarily?
If they're back to back.
Exactly.
Okay.
Does that make sense? Do people see what we're
Mm,
talking about?
Right,
So
right. Okay.
So if there's multiple A's, you can delete any of them, but that doesn't necessarily, the deletion of different A's does not necessarily result in different strings occurring from them,
Yeah.
right? Because
Oh, I see.
if I have B, A, B, deleting either of these A's gets me B, A, B, even though there were 2 A's I can delete. Whereas if I have A, B, A, then this results actually in A, B, and B, A. right?
Ah, okay.
So, yeah. Another time where you have to get like to definitions, right? And that sets, are going to remove repeat elements. And so if you were asked like a question about the size of a set based on something, then these are the sorts of then, you might think like, oh, it's the number of like strings with A's in them times like the number of A's in them or something is like the size of this other set, but it's actually, we don't know, it's a range. The size of this L prime with respect to the size of L could vary wildly. Anyways.
Thank you so much for helping us.
No problem. Good
Wait
luck
for us.
tomorrow.
Yeah, honestly though, I always like tweak on tests, so I'm just like hoping like I don't blank out. I don't
Yeah,
know. It always
it's-
happens to me.
It's hard. I mean, one of the best things to do. There was a teacher I had who passed on a lesson from their teacher, which is always look at every question on the exam before you start answering them,
Fair.
Yeah.
because the easiest questions are not necessarily the first questions, and the easiest questions for you are not necessarily the easiest questions because you'll remember some things and forget others.
Yeah.
And
Fair.
I had a teacher whose teacher felt so strongly about this that they gave an exam, and basically everyone sits down for it, and it's like the finalers. It's the final, yeah.
Yeah.
They gave a final, and everyone sits down for it, and and then one person jumps out of their seat, runs to the person's desk, and slams their paper down. It's like yes, and then
What?
like another group of the class start going oh, and like you start hearing all these groans. Everyone's like what? And then once people got to the last page, it says first person to sign their name on this test and turn it in gets full credit. Because they wanted to incentivize people looking at the whole exam. So
We did something like that.
Oh my god.
that is not on this. I will confirm that is not the case
Okay,
on
but
this
that's
exam.
a good. I'll never forget that story.
But it's a good story, and it's honestly it is very good advice, and it, like, start to set, like, some limits for yourself on, like, time on a question, too,
Yeah.
because I've worked on a question for 10 minutes,
Yeah.
because I thought I understood it, and then gotten stuck on some corner cases,
Yeah.
and then I just move on,
Right.
and sometimes just taking a break from it helped, and sometimes some of the other questions basically give you some information about the
That's
part you were
true.
confused
That's
about.
true.
Does that make sense? Like,
Right.
you know, don't, and also there's definitely a benefit to not getting super stressed out
That's
early in the
true.
exam, right? Like,
That's true.
if you get stuck on one question and you look and you've lost half your time and you're still in the first question, it's very demoralizing,
That's true.
right? And it makes it really hard to, like, be as strong as you feel you should be on the
That's
exam.
true. That's true.
And so, just kind of like looking at all the questions, then like going easiest to hardest to make sure you get the points you know you can
That's
get. And if
true.
you get stuck for too long, like don't not think about something critically for a little bit. Like it's worth like spending a couple of minutes sometimes on like something,
Right.
but like don't get stuck forever on anything. Just move on and like try other things. And that's personally how I like taking tests.
I agree with that. I think that's good.
so
advice.
Everyone is very different on these
That's
sorts of
true.
things, so it's definitely not universal. But
That's smart. That's really smart.
all right, good luck
Thank you
tomorrow,
so
guys.
much.
Thank you so much.
Can I ask a question about grading?
Sure.
He said.
Let me turn this off. Though.
Oh
I
yeah.
don't like
Okay.